In this video, I want to talk about a higher order function that we have not really been discussing so far, and that is function composition. But I also more generally want to discuss the notion that we are now getting more and more into a stage where we can, instead of defining functions from scratch using pattern matching, also just instantiate patterns, that is higher order functions that we already know. In the first set of assignments, we've seen a function that was called sumEvenSquares, where the idea was that we take a list of integers, and then we want to basically check whether the integers are even, and if they're even, we want to square them, and then we want to sum up all the square numbers. So in the first set of assignments, the task was to define this from scratch using pattern matching, using the standard design pattern on lists. So basically to have a case for the empty list here, and to have a case for the non-empty list, and then to use recursion, and to perhaps use the function even, but not to use any other higher order functions. But of course, we have now seen sufficiently many functions that we can do this. We have seen functions such as sum and filter and map. And with these, we can just recognize that this is essentially a combination of these functions. So if we start out with a list of integers, and we want to know which of these integers are the even integers, then you should immediately think about filter. Filter is the way to reduce a list in scope to only the elements that we are interested in. Right, so we can start by saying filter even access, and then at that point we have a list of integers, which we still have to transform further into the final int. Right? But at this point, we now have a list of integers that is guaranteed to be even. All right? And now we want to square all these integers that are left in the list at this point. Right, so how do we do this? Well, if we want to do something for every element in a list, then you should immediately think map. Right, so you can say map, and the function that we're mapping is the function that squares an integer. So, and that is best written just as a lambda term. And then again, this doesn't have the right result type yet, so we still have to apply something to the result of this function. And again, we are still left with a list of integers, but this now contains the even square numbers, right? And we want to sum them all up. And for this, we have the function sum that does it. So perhaps long enough to put it on a new line, but this is our end definition. And this is a one-line definition, right? And the whole point of being able to instantiate functions that we already have seen and combine them in such a way is usually that we can, rather than do a definition by case distinction, we can now give a definition in one go. Often these definitions are actually called one-liners, even though they can get so long that they don't really span one line. But the idea is that we are not required to do a case distinction anymore, because all the underlying logic that would require case distinctions is now captured by other functions, such as filter and map, and sum in this case. Okay, but there is also something about this function that is interesting, namely that this XS here, this list XS, it only is used as the input to this innermost function here, the call to filter. And then the result of the call to filter is fed to the call to map. And then the result of the call to map is fed to the call to sum, and that is the end result of the total function. So we have a little bit of a pipeline here that flows from the right to the left syntactically. So our input enters at the right, and then we have this call to filter, and then the result of that goes on to the call to map, and then the result goes on to the call to sum. And this happens quite often. So this is a pattern that arises quite often, that an input is going into one function, and then the output of that function is going into the next function, and that is possibly repeated. And it does make sense to give this pattern a name, and that name is function composition. So the idea of function composition is that if we have two functions, we can compose them using an operator. And actually this operator is predefined, so I should hide it from the prelude. So we are defining the composition of f and g, and that is supposed to be the function that takes an input x and then first calls g on x and then calls f on the result of g of x. And this is exactly this pipeline that I've just been describing, but here we are only looking at two functions, right? So the idea is that the input x goes into one function, which is called g, right? That you can think of that as being the filter even call here. The excess goes into the filter even call, right? And then the result of that is being passed to the next function. That is, in this case here, up here, it's map lambda x arrow x times x, and here this is called f in general. And that is then composition. And we see that type inference works for us here. Exceptionally, I did not start from the type signature because I really just wanted to show that this is the pattern we want to capture, right? The inferred type is correct, but it is a little bit difficult to read because of the chosen type variable names. So let's try to do this ourselves, perhaps. Let's try to come up with the type signature of dot ourselves. So the type of x, right? So let's say first of all we have two functions here, f and g, as inputs. So we have something of the form dot 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 to dot dot dot. So this first thing is the type of f, right? The second thing is the type of g, and then we have a result. Okay. And now we know more things. So the type of x here that's coming in here, let's call that a, right? So the result is a function because we use a lambda term here. So we write a to something, and a is the type of x. And now x is being used as the input of the function g. So g, that is the second argument of dot, that is this one, is also a function. And g takes something of type a as well, because we pass the x to it. It must take something of type a. Right? And let's just assume that the result type of g is b. Okay. Now, that means then that g of x here is of type b, and we pass that to f. So f, that's the first argument of the dot operator, also has to be a function, and it has to take a b because we pass the result of g of x to it. And then let's just assume that it goes to some type c, right? And f of g of x is then the result of this function that we're returning here on the right hand side. So it's the result type here. So you can see composition, right, as combining two functions into one function. And the two functions have to be type compatible in such a way that one goes from a to b and the other goes further from b to c. And then we can go directly from a to c. But the flow was sort of reversed, because like in function application syntax, we typically write the function argument to the right of the function that we apply it to, and for composition we kind of keep that order so that we go from A to B with the right operator of the composition function, and from B to C with the left operand of the composition function. There's no need to write this as a function application, so you could put the x on the left-hand side by putting this in parentheses and putting the x over on the left-hand side as usual. That would also work. Right? That's a different way of writing the same definition. You could also omit these final parentheses because it's never needed, right? The function arrow associates to the right, and actually this type signature more closely corresponds to this kind of definition where we pick up the a as an extra argument here on the left-hand side. But perhaps let's leave it as we originally had it, because it makes the standard view here more obvious, namely that we compose two functions and create a new function, and then we have to remove the parentheses here. They're not actually allowed if we don't have any extra arguments. That's a little bit of a strange corner case. Then GHC does not allow having parentheses here if there are no following arguments. Okay, so that's our function, composition function, and that exists in the prelude. That is defined in exactly the same way. So if you look at what's the type of the prelude version of dot, so that's actually also a strange syntactic thing. If you want to have a qualified version of an operator, then you write prelude dot as the prefix for the module you want to refer to, and then dot is the name of the operator, and then you still have to put the whole thing in parentheses because we're using it in isolation. And you can see that we get the same type signature, and actually even with the same choice of variable names, but with the final pair of parentheses omitted, because that's the simpler form with fewer parentheses that GHC usually prefers to use when printing things. And now we can also alternatively write sumEvenSquares using function composition. As I've already said, we can spot this pattern in sumEvenSquares, and we can say, let's perhaps make a copy of this. What we can observe here is that we really have an instantiation of this pattern if we consider the partial application of filter even. I'm adding an extra redundant pair of parentheses here for emphasis. So filter even is our function g. So that's the first function that the XS goes in. And then map applied to the squaring function. I'm adding another redundant pair of parentheses here, is our function f. That's the second function this is going in. All right, so this is exactly this form, that this is something that's depending on an XS. So so we can as well write this as the composition. Oh, I have to be a bit careful with the parentheses. Let's remove a couple again so that I can still even read what I'm writing. We can write this part here as the composition of map of the squaring functions with filter and even. And this composition of the two functions is then applied to XS. Now at this point, I don't think this looks much better, right? So they mean the same thing. You can expand the definition of the composition function here using equational reasoning, right? So if you if you expand the composition again to this lambda abstraction and then it gets applied to the XS, you end up with exactly the code that we originally had. But now we can spot the same pattern again. Now we can see that the XS is going into this composed function here. Right, so that now plays the role of our G. And then the result of that is passed to sum. So that plays the role of our F. So we have another composition. So we can also write this like this. And then you can observe that it does not really matter for function composition in which order you bracket compositions. So function composition is an associative operator. So we don't actually need these parentheses here. So we now have a composition of 3 functions. And that is the point where I think it becomes slightly better already than the original, because we can now really see we have a pipeline, and we can see that immediately. Right? We have a pipeline where we feed in the XS, and then what are the stages we run this through? We first filter out the even functions, then we map with the squaring function, and then we sum, all on the result of the previous one. But we can actually do one further simplification step here, namely that we can now observe that we don't really need to mention the XS at all anymore. We can actually get rid of the XS here, and we can get rid of the XS here, because all it's doing is this argument is appearing as the final argument to whatever we're defining here on the right-hand side. It's not being used anywhere else. So actually, we can just look at the composition itself. What we have to define here is a function from list of int to int, and the result of the composition is a function from list of int to int. We never even need to explicitly mention the argument. And I think that is the point where I would say this is slightly nicer than the upper one. It's perfectly okay if you use the upper definition, but the lower, I think, is slightly nicer because it makes it clear that you have this pipeline situation where you start by doing filter even, then you map the square function, and then in the end you sum over the results. Okay, so let's look at a similar example, perhaps. Let's try to define a function which in a list of strings, or perhaps even more generally in a list of lists, okay, counts all the elements of the outer list that have a length greater than, I don't know, greater than 5. Right? So let's call this countLongerThanFive. I mean, this is not something that would arise as a general function, but it is something that you might need in a concrete application, where you, for some reason, for example, you want to run something against a particular process, and running running with small inputs is free. But running with long inputs costs something, so we have to identify how many long inputs we have in order to determine the total cost, or something like this. Right? So and the idea was originally that we do this with a list of strings, but actually we are not going to use anything that is particular to strings, so we could just use this with a list of A's. And again, we want to go to an int here. And once more, this is a function where we could start defining the whole thing using pattern matching just from scratch. We could traverse the list. We could look at in the cons case, we could look at the first element of the list. We could check whether that first element of the list has a length that is greater than 5, and if it does, then we increment a counter, otherwise we don't, or if it does, we add 1 to the, like, we generate a +1 result, and otherwise we don't, right? So but we can also do this again by combination of other functions that we already have. It's always good to think about intermediate data structures that would be useful to have. So if we start with this list of all our lists of lists, right? Probably one useful intermediate data structure we would have is to simply get rid of all the ones that are not at least 5 elements long, right? To only keep the interesting results. And that is again filter, right? So we can again start by giving a name to the argument, and we can again do a call to filter. And let's leave the function that we want to filter with open for the time being. So that's the function that should check whether an element of the inner list is having length at least 5. So let's do that now. So this inner list is still a list. So x is still a list. So we want to check whether the length of x is greater than 5. Okay. And then, what do we want to do then? Then we want to not sum them in this case, right? Because we don't have necessarily numbers in them, but we want to just count them. So what's left is a list, and if we want to count the number of elements that are left in the list, we want to compute the length once more. So we get this. And at this point, we again see that we have a function composition of 2 functions. The first is this call to filter, and the second is this call to length. So we can rewrite this as a function composition of length and filter, where the access is being passed at the very end. And now again we have the situation where the access is picked up here and applied just at the very, very end, and it's appearing nowhere else. So we don't even need to do this. We can just look at the composition of these 2 functions immediately. And we can just say we first do the filtering and then we do the length. And it's another good example of a function composition. Now, when people start getting fond of function compositions, they start spotting them everywhere, and one could continue here. I just want to point this out as an option and say that if one looks closely, then actually this argument to filter can also be seen as a function composition. Because really what we do is we take the x and we feed it to the length function, right? So we first compute the length, and then the result of length of x is being compared with 5. Right, so we can do this in multiple rewriting steps in order to make this more explicit. So we are applying this function here where we compare something with whether something is greater than or equal to 5. If we want to make that more precise, we can write this as a separate function specifically that takes an argument y and compares y whether it is greater than 5. And then we apply this function here to length x. And this does the same thing. Right? Actually, I should have, at least at some point, I should have tried my functions. So count longer than 5, does it even do what I want? So if I do, for example, use my name and Haskell and I don't know, course and I need a short. I need something shorter, right? I mean, these are all longer than 5. Let's just do X and Y, and let's do a foo here. So there should be, the result should be 3, I guess. Yeah, okay. And let's do some even squares as well. 1, 2, 3, 4. That gives us 20. That is plausible because 4 plus 16 is 20. Yeah. And some even squares prime has the same result. Okay, so back to count longer than 5. So we are at this point now where we have rewritten this in sort of worse form, but now we could see that this is a partial application of an operator, of the greater than or equals operator, so we can write this one as an operator section. So that makes it already a bit easier. And now it is actually relatively clearly in the form of a function composition again, right? It has exactly this shape here, where greater than or equal to 5, this operator section plays the role of f, and length plays the role of g. So what we can do is we can write this as a function composition as well. Now, as usual, I would say tastes differ, and also what people consider readable or not differs a little bit from person to person, and from their own personal taste, but also from the degree of proficiency they already have with Haskell, how comfortable they feel with various different concepts, how they personally think about certain things. So some people are very fond of writing everything that can be turned into some form of function composition in the form of a function composition. There is even a name called point-free, or sometimes pointless style, where the idea is that the function argument is referred to as a point, and because we are not even mentioning the function argument anymore in this shape, you can call this point-free style, and it is possible to rewrite basically any function into point-free style. But some functions benefit, I would say. Some functions become clearer and nicer to read. Other functions are becoming, I would say, much more complicated to read. And you should apply some form of common sense, I think, and your own, let yourself be guided by your own idea of what is easier and what is harder. So use function composition by all means if it helps to make the structure clearer, but don't do it if you personally think that it doesn't. Okay, I think that is enough for the time being about function composition. It is, however, useful in this context to briefly mention a few other functions. So let's do that towards the end of this video. So one other function that we have not very explicitly been discussing so far is the identity function. So that is a nice little function that is available in the prelude as well. The identity function is of type A to A, and it is utterly unspectacular. So if we wanted to define this ourselves, it would just be the function that takes an argument and returns itself. And of course, if we want to use our redefined version of the identity, I also have to hide it from the prelude. The identity function is a little bit funny in the sense that you might first wonder, why is it useful at all? Right? So, but just as 0 as a number is useful in certain cases, the identity function as a function is also useful in certain cases, as a base case for something, or as an instantiation of something where you are given a degree of flexibility. So in case of a higher order function, you can, if you have a place where you can fill in a function, you can always ask yourself what happens if you fill in the identity function. So let's use a few examples of that. So in the case of map, it's not very spectacular. So if we feed the identity function to the map function, then we take a list to itself. Then this is the identity function becomes the function that we apply to every element in the list, and then the resulting list is exactly the same as the original list. So this is actually a law that holds for the map function that that you can even rely on. But it doesn't mean that mapping the identity function is particularly interesting in practice. But you know that mapping the identity function over a list is always going to be the same as the original list. Okay, and we can prove this by equational reasoning, by doing induction on all the possible shapes of lists, right? Starting with the empty list and then going through the cons constructor, and one can prove this. This holds for the definition of map on lists that we have. But it is also rather obvious. But we have some other functions, again, partially functions that we have not been looking at in all too much detail yet, but that are having interesting relationships. So there is a function all, and this is the foldable form, but let's restrict it to lists. So all is a little bit like filter in the sense that it also takes a function from a to bool as an argument, right? And then it takes a list of a's, and then it returns a bool. And we can use all with some predicate. So we can use even as an example again to check whether all elements in a list satisfy a particular predicate. So I can do this. So if I really have a list of only even numbers, then this says true. But if I have just one number that is not even, then the result will be false. Okay. And there are many interesting relationships between different functions now. So we also have the function and, which is, again, if we restrict it to the list case, is taking a list of booleans to a boolean. And is simply a generalization of the logical AND operator, of the binary logical AND operator to a list of inputs. So if we do AND on now a list of booleans, and if I have any occurrences of false there, then it's always going to give us false. But if I have a list where all elements are true, then it is going to give us true as the result. And we can ask ourselves, how can we define AND if we already have all? And interestingly, we will observe that if I hide AND here, let's only focus on the list version, you can see that AND is the same as all applied to the identity function. Because, right, if we consider all, which takes this predicate, if we feed the identity function here, this forces that the original argument that we pass here, the element type of the list, must already be Boolean, because the identity function goes from one type to itself. And if the result type is Boolean, then the input type must be Boolean. So we are now expecting a list of Booleans, And the predicate that every element has to satisfy is the identity predicate. So the Boolean itself that is in the list has to be true, and that is exactly what AND does. Right? So the identity function is useful in a number of places. Right? Now we can ask about other things as well, right? I mean, so there are there's a similar relationship between the any function and the or function, but I'd rather look at the identity function a little bit more. So another interesting property of the identity function that is a bit surprising is that the identity function is a way to denote function application, an explicit way to denote function application. Right? So what happens if we apply the identity function to a function? So if we apply the identity function to not, then we get the not function back, right? The identity function doesn't do anything if we apply it to an argument. So if we apply it to a function argument, we are just getting the function back, right? And if we apply the identity function applied to a function to another argument, let's say true, then we just get the result of the function application. Right? So this is just false. So one way we can write not is applied to true, which is admittedly terribly obfuscated, right? So, but is to say not and then ID within backticks applied to true. So this is denoting function application, because what we're really doing is we are applying the identity function to the not function, getting the not function back, and then we're getting true back. Okay. Sometimes it is useful to have an explicit name for function application. Right? Because we might, for example, want to do an operator section. So we might want to say that we want to apply a list of functions to a certain argument. If we have a list of functions and we want to apply them all to a certain argument, then we might want to have an operator section for function application. So if we have a list of functions, let's say all from int to int. So here we have, let's just say +1 times 2 +7 times 4. Right? And we want to apply all these functions to the number 3. Then we can do this using map, and we can obviously write this using a lambda abstraction. So we can say we get a function out of this list and we want to apply the function to 3. That would be one possible way of doing this. But we could also use ID3, as we've just seen, because we can use the identity operator as an explicit name for function application. Now, because this is indeed a little bit obscure, there is a different function that is being used for this in Haskell, and that is called the $operator. And the $operator is a restricted form of the identity function that is really just limited to the function application. So rather than going from A to A, it is going just from a function of A to B and is giving us back a function of A to B. Or if we drop the parentheses equivalently, it is taking a function and an argument and giving us the result. So this is exactly the type of function application as we expected. Right? And there are multiple ways to define the dollar operator. As we've just seen, we can just use the identity function because we can just take a function and return the function itself, and that works. Right? But another, perhaps more readable way is to say, if we take a function and an argument, we just apply f to x. And then we can use the dollar operator in a section. Oh, now I should hide the prelude version of the dollar operator as well. To get this application done. And this actually exists, right? I mean, the identity function also exists, but using the identity function in the special cases, like a meaning function application, is a little bit misleading. I would not recommend it. It's just an interesting realization that it actually works that way. But the dollar operator is specifically there to denote an explicit form of function application. And the dollar operator is also being used to save parentheses from time to time in the Haskell world, because the dollar operator is given a very peculiar priority, namely it's defined to be right associative and extremely low priority, whereas normal function application written as a space has the highest priority and is left associative. So because the priority of dollar is so low, it is often a way of saving parentheses. Let's perhaps look at an example of this. Perhaps go back to our sumEvenSquares function. So you can see that the original sumEvenSquares function has extra parentheses around this call here for map and this call here for filter. Right? And that is exactly coming from the fact that function application is left associative. Right? So because we want to apply sum to the entire result of this call, and so we have to group it. Right? But if we now use a right associative low priority operator that is written as a dollar here, then we can get rid of this pair of parentheses and write it in the same way. And similarly, rather than putting the parentheses around this call, we can use another application of the dollar operator and get rid of that pair of parentheses. So if you see a dollar anywhere in Haskell code, it just means function application. But it does behave differently with respect to the priority of the operator. And the motivation for this is usually to avoid introducing parentheses that scope over a really long part of the code. And sometimes if you've already written a large blob of code that fits together nicely and you just want to apply a single function to all of it, right, then rather than having to put parentheses around the whole block of code, you can just apply the function and use a dollar. But again, like with the other things that we've been discussing, this is sort of a little bit of a matter of taste, and sometimes it makes things more readable, sometimes it makes things less readable. It's something you have to apply your own feeling as to whether you want to use it or not, right? But at least you should be able to not get confused and to like if you see this in other people's code. Now it can be a little bit confusing to understand the exact relationship between all these functions that we've now been discussing. In particular, the exact relationship between function application and function composition. That can be confusing at first. That you think that, like here, it almost looks like we can like replace dollar and dot, right? But the important difference is still that here we mention the argument and here we don't. So there is a difference, right, between function application and function composition. because function composition does exactly that. It abstracts from its argument. So there are subtle differences here, and they may be confusing at first, but the best way to fight this is to just practice. Just like look at a lot of code, to write a lot of code, to try out different ways of expressing things, and to over time become more confident in all this. Okay, that's it. Thank you.